Okay, if you were just doing policy learning instead of value function learning, your first idea couldn't even have been a linear function approximation. It had to be some sort of a logistic regression, because you need to take a continuous quantity and map it into 4 discrete values, up, down, left, right. So is everybody completely clear on regression versus classification now? Given a problem, can you tell whether it's a regression or a classification? So given your homework and test scores, I am predicting your grade. Is that regression or classification? How many of you think it is classification?
8% or letter.
Letter grade. What do you guys want? Did you see letter grades? Okay, so how many of you think it is a classification? Okay. By the way, it's for those of you in the very back, you do realize that I can see that you're not paying attention, right? And I also know your faces. Please don't play this game with me. Okay. Okay. So how many of you think it is classification? How many think it is regression? Okay. Why do you think it's regression?
Because essentially we are trying to calculate a grade based on like the linear values, linear feature values.
No, but that's not enough. If I just do the linear thing, then I will get infinite number of grades.
Yeah, but
I'm converting the grade into A, B, C, D, or A plus A minus, B plus BB minus, C plus CC minus D, or whatever.
But each of the grade will have some numerical equivalents, right? So
no, but I'm putting, okay, so remember what do you guys ask when you don't get the grade you want? What do you want to know?
cutoff.
Where is the cutoff? Where is this cutoff business? The cutoff is threshold. Thresholding essentially is putting nonlinearity into stuff that was completely fine. I mean, really, do we believe that there is a difference between 81.9 and 82.1? No. But when I convert them into grades, they may actually have discrete jumps. So grading is a classification scheme. Right? Using your same inputs as your exam scores, etc., I'm trying to predict your cumulative total. Is that a regression or a classification? Regression. So you understand that. Okay. Now it turns out that both of them essentially are still learning a function. In one case, you're learning a function that basically maps you into full real number range. In another case, you're learning a function which maps you into some discrete set of values. Okay, and to have discrete set of values, if you have a linear function, a linear input, and then if you have continuous input, you want to show it to a discrete set of values, you need some kind of a thresholding in there. Okay, so that's something that you want to keep in mind. So regression versus classification, and they're actually quite closely connected. Okay, and in fact, the connection is in terms of this G. You have to throw in a G function, otherwise you won't work. Okay, now perceptrons can do regression. You already know this now, because we just did, the value function approximation using linear functions, and I showed you can think of the linear function essentially as a linear perceptron. But they can also actually do classification. Why? Because they'll allow G function to be thrown. Okay, so that's what I'm going to show you next. So that basically, and as I said, this is the brain connection. Essentially, individual units have some nonlinear function. Nonlinear function typically has this thresholding, gating characteristic. At least biologically, that seems to be true. Okay. Now again, having said, and then here you actually show the step function is a thresholding function. Psi function -1 plus 1 is also a thresholding function, but these two are discontinuous. Actually, yeah, they're discontinuous. Okay? Whereas sigmoid is differentiable, so is tan h. Another differentiable function is tan h, which could look like this. Okay? And in the beginning, mostly people used to use either sigmoid or tanh. Here is an interesting thing. These days, if you actually look at neural networks, they use something different. They use something called ReLU. ReLU is a rectified linear unit. A rectified linear unit essentially basically takes the value to be x, when f of x equal to x if x is positive, equal to 0 if x is negative. Okay, now here is an interesting question, and it's not hard to actually find continuous versions of the rectified linear units, which would sort of look, I guess, this will become smooth, the kink would go away and it becomes smooth. Now, before going forward, I ask you to think what possibly can be different between these, let's say these two, which are continuous functions, and this. It turns out, and I'm just telling you now, it will come back to you later on, one problem in general with these units is that the differential at this point is how much? What is the derivative of this function at this point? How many of you could see that like right away? And how many of you started very quickly doing differentiation of 1 by 1 plus equal minus x? You do realize that the derivative is nothing but the slope. And the horizontal lines have 0 slope. Right? Okay? And so sigmoid function, tanh function, anything which at all looks like a gate, actually is going to have 0 derivative for most of its life, except in the region around origin. On this side as well as that side, if you go a little farther, it will become 0. Is that a problem? Turns out it could be a problem because you're doing all the updates in some quantity that is proportional to the derivative. If in most of the parts of the world the derivative is 0, then, and if you get into, by mistake, your weights have put you in region like here or here, then trying to change, you will make 0-sized steps, infinite number of times. Infinite number of 0-sized steps are still 0 size. So you don't go nowhere. Do you see what I'm saying? By the way, how many of you know amplifiers? How many of you have heard this annoying sound every once in a while when people are trying to talk on the feedback? Amplifiers also actually, for example, many of the interesting things in life, they have an operating region. Amplifiers actually have a nice linear amplification characteristic on a small region. If you push input bigger than that, they just saturate. It's the saturation that you hear as noise, and then you wake up at that. Right? You can saturate threshold units of sigmoid and tanh. And when they get saturated, there is nothing you can do. Now notice what's happening here. In essence, even though the overall function does have a global minimum, you are stuck somewhere here and you are making 0-sized steps to get to this global minimum. So you will never get there. For the longest time in neural networks research, people only considered tanh and sigmoid as the gating functions. And would be surprised that nothing is converging, especially if you have neural networks are very deep. That means the input is connected to many layers of these neural units, these perceptrons to the output. You're trying to compute the gradient when you change the input. And the gradient with respect, the gradient of the function with respect to the inputs. That gradient signal, they call it signal, the gradient signal that we'll see, it has to get back propagated. We'll see that today. That back propagated signal becomes 0 very quickly. And when it becomes 0, nothing is going to happen. Even though the problem theoretically has a solution, the way you're doing it is not going to get you anywhere. So instead, then you do something like ReLU, which doesn't become 0, at least on one side. Okay, how did people figure this out? After they tried it, it worked, then they made this theory that, yeah, that's what must have been happening all our lives. Okay, by the way, we'll see at some point of time that, neural networks have been tried multiple times back in 60s when, a guy called Rosenblatt, Frank Rosenblatt, tried them. He was a Cornell guy, and he did the single unit perceptrons, and there was a lot of, enthusiasm about that. And then, of course, a couple of people, Minsky, who's one of the founding fathers of AI, and Papert, basically said, look guys, just with a single layer of perceptrons, how many ever you have, you will only learn linear functions of the inputs. And we'll see why in a minute. Okay? And that if you want to learn all functions, then it won't work. And then, so for a long time, people started doing that, and back in again in the 80s, basically people started realizing that yes, we can train the multi-layer perceptrons, multi-layer perceptron networks, and the idea would be exactly the same. You just do the same gradient descent. Previously, people just got surprised. Oh, there's too many layers. What do we do? We just leave, and then went away. This is how science works. People collectively get demoralized, go away somewhere. And then something is working, they all get collectively overly, like stock market bubbles. Right now we are in deep learning stock market bubble. Okay. And so, like other tulip fever, whatever. And so right now there are a large number of people working. In 80s, essentially, they tried actually doing the multi-layer neural networks, and they found that the convergence is extremely slow. And then a bunch of small things, as well as a bunch of actual changes in the world, such as a lot more data available, a lot more GPUs available have happened. And starting around 2011, again, one of the few small theoretical things that changed is realizing, for example, that using ReLU is better than using sigmoid and damage. It's not a huge big idea. In fact, just with itself, you wouldn't have had a deep learning revolution. That's what we important. And the reason it's important is the gradient becomes 0. And the gradient becomes 0, you are propagating zeros, nothing is going to change. Okay? Now again, another way of thinking about it is, the worst way to do hill climbing is I put you in, like say right now in Phoenix and say, go up to San Francisco peaks. The problem is all around you is this flat terrain. Which direction is supposed to be taken? They're all 0. So you just pick one randomly. And if you pick one randomly, the chance that you'll actually go towards eventually a path where the ground starts raising, and then you will be either on top of San Francisco peaks or at least a minor peak like Superstition peaks. It's going to be much, much later. You see what I'm saying? So what I need to do to make sure that you will go up to Superstition peaks while using gradient descent is to first construct roads such that they slowly slope up towards Superstition mountains. So I change the environment around you so that it has a nice slope. And then you know that, okay, that's obviously increasing my height, and then I keep going towards that direction. And then I'll go top of the Superstition. Another example is kitchen sink. What is the nirvana of kitchen sink? The water needs to go into the hole in the middle. Right? I have seen in my life great kitchen sinks where they will have this undulating pattern. Or even the pattern where the sink actually slopes away from the hole. There is nothing wrong at some level about that particular kitchen sink. Eventually you can take all the water and pour it in the middle. But water basically follows local gradients. Water follows local gradients. Right? And if you don't set the gradient such that the local gradient is globally consistent, then you will have a bizarro kitchen sink. Okay, so these are all things that are connected to basically gradient descent, obviously. Okay, Okay, so by the way, so for the single unit perceptron networks, so this is one thing that we already talked about. You could also, this is also called single layer perceptron network, where inputs are connected to multiple different perceptron units. This is still considered one layer because a perceptron's output is never becoming the input of another perceptron. Do you see what I'm saying? Now, why would I use this? You might have something like a multi-class classification problem. So, in fact, one idea is I could have used this to some extent to decide whether I should go up or down or left or right in the policy function. So, one perceptron only learns whether I should be going up now. Another perceptron only learns whether I'm supposed to be going down. And so the output would be 0, 1, 0, 0, 0, 0, 0, 1, 1, 0, 0, 0, 0, 0, 0, 1. Those are the outputs, and it correspond to the 4 different actions. Okay, so that's how you would actually take single unit perceptrons with a little bit of non-linearity, the G value, the G function, and then learn actually policies. AlphaGo basically learns policy networks best. Except it does deeper ones, but we can see. I'll skip that part. Now, I'm going to now drag you through one more gradient computation example. You have to get used to gradient, okay, essentially. So, I'm mostly doing the same thing as what I did for the linear sum of features, okay? Except this time, I realized that there is a G function, which is a threshold function. In the previous example, G was just identity function. That means it took the weighted sum and gave it out. Now the G can be any arbitrary function. It could be sigmoid, it can be tan H, it could be ReLU, any other. Okay, so I want you to understand that these two can be done. And so imagine again that we are essentially trying to minimize the sum of errors, sum of squared errors. That's called, basically it's called the mean squared error or the sum of squared errors. We want to minimize that. Okay, so this is my perceptron unit and these are the inputs. Okay, now I'm basically using slightly different notation instead of theta and F. Now I'm using W and I. W's are the thetas from previous step. And F's, and then I inputs are the features F from the previous step. But the notation is different, but everything else is. Okay? So essentially, I want to take the true value for a particular input T minus the output value O that actually the network gave for the set of examples here. Okay? And then that would be T minus O. And then I separate it. I sum these errors all over all the examples and basically do my half. And then I want to minimize it. Now if I actually write it down, this is how it looks. So T minus the O becomes G of weighted sum of the inputs. Do people see that? Previously there was no G, now there is a G, that's it. Now this is where the chain rule of differentiation is the hero of this entire stuff. You throw in a zero, G essentially just has, you have to also differentiate G, that's it. Okay, nothing changes, even though obviously underneath it all, a large number of things have changed. Now you have a nonlinear function operating on inputs, and so in fact, it can push the continuous input space into discrete output space, which is classification. Right? Okay, so that's what that is. And then, so now I want to decide how to change the weight Wj. To change the weight Wj, I need to compute the partial derivative of the error with respect to Wj. Okay, and that would be obviously, so first of all, so you have to do multiple steps here. So one part is this whole thing is squared, so the 2 get cancelled out and the whole inside thing will be there as one part of the derivative, t minus 4. And the other part is the derivative g dash of this input. Remember in the past case, I just had the derivative of just the inside. Now I just have the derivative g dash of the linear sum input. Okay? Right? Now, what that basically means is then, so essentially, so this is my derivative, gradient obviously, so w should then be changed by wj. Because the derivative is negative, I have to take the negative of that in making the change. Okay? Wj plus ij times t minus o times g dash. And in fact, normally you put an alpha. Okay? Now g dash of wj will itself become essentially, if you, then you have to actually differentiate the inside and differentiate the outside. When you differentiated the inside, oh sorry, actually I forgot. The reason this ij came is when you differentiated the inside with respect to wj, the only part that will survive is wjij, which gets differentiated with respect to wj, you get ij. You see what I'm saying? So you had the ij part, you have the error part, and you have this extra quantity that you didn't have the last time around. This quantity is g dash of the input, and the g dash of the sum input. Now, in fact, this quantity was 1 previously, because in previously g of x is x, g dash of x is 1. Right? Now it will be something different. So this is where, by the way, I made you go through that partial derivatives review example. It turns out that, not that important, but it turns out that sigmoid function has this nice little property, cute little property, which is that g dash of the sigmoid function is equal to g of x times 1 minus g of x. So you can just basically, if you know the value g of x, so if you want the g dash of the same value, g dash of the function at the same point, then you just take the g of x times 1 minus g of x. The thing that I hope you understand is these are all numbers. Okay? And so essentially you are updating w towards these numbers. W in the direction of those, whatever this particular vector is. Okay? So you basically have the same sort of update rule. Okay? Except this update has more factors. There is a g dash factor. Okay? So you can actually say wj is wj times alpha times error times g dash times ij. This alpha, of course, is the error. And if you do this, now this thing works for any arbitrary g, including sigmoid functions, which means you can do, this is a proof that perceptrons will also work for example, binary classification tasks. What's a binary classification task? You have input and I want to say pass or fail. You know, here is your cumulative weighted sum of your grades. At the end of the course, I am deciding pass or fail. That's just 1 or 0. So if I do sigmoid function, I can actually get that. More or less, right? Because it only has 2 values here. There is this middle part where it is slightly different. In fact, one of the funny things is that because irrespective of the input, sigmoid function maps stuff into 0, 1 region, right? It will be mapping it to 0, 1 region. You can, and what else do you know? What other functions do you know where their values are always in the 0, 1 region? Yeah?
Trigonometric functions?
What?
Trigonometric functions like sine and cosine. Well, those are
That's
negative.
true, but even bigger than that. Trigonometric functions are 0, but sine and cos are. Tan is not, obviously.
Yeah.
And actually they're between -1 and 1,
Yeah.
not 0 and 1. So things that are always between 0 and 1. You took a course on this stuff. Probabilities. Do you see what I'm saying? Remember the, you know, if it, if it quacks like a duck and looks like a duck, it's a duck kind of a thing. So if it looks like these numbers are going to be between 0 and 1, we'll call them probabilities. And in fact, what comes out of the sigmoid function can be interpreted as the probability that the input corresponds to class 1. And so that it will, the 1 minus of that will be the input belongs to class 2. And keep this in mind because in a minute we'll talk about, actually sometimes you might want to just work on those probabilities rather than just directly talk about predicting. You see what I'm saying? Okay, sigmoid gives you 0 and 1, 0 and 1s are probabilities, so let's call them probabilities. And that's actually what's done multiple times. That's one of the reasons that people love sigmoids, yes?
Is there like a more rigorous statistical backing behind that? Or is
You will have to live until Bayes networks.
Okay.
All rigorous statistical background for machine learning comes from probability and statistics. Okay. Except now, in fact, so there is a book by François Chollet that I was looking at over the last couple of days. François Chollet is this guy who's pretty well known in the deep learning community right now. And he wrote this book on basically deep learning with Keras. Keras is a top end for multiple deep learning software substrates, one of which is TensorFlow that we'll be seeing in a minute. And then there's Theano, which is not being used, and then there's PyTorch, which Facebook pushes, TensorFlow is pushed by Google. And so if you don't want to know any of these, then you can live in this Keras, and Keras will compile it down to these specific software things. And François Chollet is the guy who wrote the Keras software. So he wrote this book on neural networks, and he says that I've decided that people don't like formulas, so I'll only put Python code. So those of you who thought, wow, that's my kind of a guy, get that book. right? So in essence, he basically, and in fact, he actually says, gradient, what's the gradient? Somebody else will calculate the gradient. We don't need to talk about it. It will be done for you. So this is actually now part of the problem with machine learning in general right now is it's like electricity. People should be able to use electricity without knowing Faraday's laws. Right? Okay. So that's what it's become. And so in fact, there are books meant for using deep learning without knowing what the heck it's doing. Okay. And this one still doesn't know what it's doing, but at least it tells you at a more informed level what exactly are the various pieces doing and why they might have some connection to actual proofs of convergence. And eventually the only thing that actually has proofs of correctness and so on are statistical. Okay. Okay. Any other questions on this? Yes?
Just want to confirm T is discrete and G of X is continuous, right? T is discrete because we are doing custom.
No, again, notice that the way we are doing this actually, T is discrete, but this whole thing is continuous. G of X is continuous. So
like we don't take it after the threshold, right? Like after, like if.
No, G is a continuous function. So.
But we also put the threshold also, right?
No, there is no separate threshold. G is the threshold. That's a very good question. There is no separate threshold. Rather than use thresholding functions like this, which are discontinuous, we use this, which looks like a thresholding function, but it's actually continuous. Okay? In fact, you can do sanity check. Okay? Remember I said g dash of x is g of x times 1 minus g of x. Right? And you know that sigmoid we already knew it is between 0 and 1. So where will the gradient be between? Between 1 and 0 again. Right? The maximum would be, let's say, one of these quantities is 1. If one of these quantities, actually it's definitely between 1 and 0. Yes, okay? And it takes, I'm sorry, wait. No, it actually, sorry, the value of the slope in the middle is actually quite high. So it's not 1 and 0, sorry, I made a mistake there. So this g of x and this 1 minus g of x, both of these are numbers between 1 and 0. And the g dash essentially is the slope of the function, and you can see that the slope would be highest in the middle here. Okay? Any other questions? Yes.
Could you use
But it's bounded, it's not infinite. Yeah, go ahead.
Could you use a cumulative beta distribution?
I'm sorry, what you said?
Could you use a cumulative beta distribution curve instead of a sigmoid function?
You can use all sorts of different distributions. I'm just basically, so obviously, in fact, that's the next slide in essence. So now you understood how to do gradient descent for very simple linear functions. You expanded it to understand how to do gradient descent for linear functions thresholded by G, where G is like the one that we paid attention to in the sigmoid function. So one thing that you notice is between the two, we always consider E, the error, to be half of T minus O squared, where T is the true value and O is the predicted value. You square it and sum it. So that, my friends, is the next slide, loss functions. Okay, in the machine learning lingo, loss is basically the objective that you're trying to minimize. Till now you have seen one loss function, which is mean squared error. You minimize that. Okay, but it's not always the case that you should only be just minimizing mean squared error. Okay, one thing that you could do, and this is actually, I just basically will point this out, that, so this was the mean squared error loss function, and you can minimize that, and then the gradient steps will change. By the way, one other thing that I want to mention is, notice that this W was Wj plus some alpha times some gradientish quantity. Right? Okay. If you looked at the update for the previous time, right? That too alpha times, the difference times some gradientish quantity. Basically, this is the gradient. So it looks as if all the little steps would be changing the weights alpha times some gradient quantity. It's the gradient that changes depending on both the error function, the T minus O part. This part came because you were squaring the error function, right? And then also, Fi part came because you are adding up the features, weighted features. And the G dash in the next one came. The G dash in the next one came because you are using a particular form of thresholding function. The point is ultimately that the workhorse is changing the weights in a direction proportional to something, some gradient of the loss function. Gradient of the loss function depends, of course, on how the loss function is defined, as well as, for example, what thresholding function you are using inside. Okay, so they all will eventually